Hello everyone, welcome to today's presentation. Today I would like to cover the materials about the metric algebra here, the metric algebra here. So what is the difference today is the specific material is from the metric algebra, some concept and principles for the econometrics at graduate level. Again, I use the implementation in the R and Julia. They are the open source software, and also proprietary or commercial software, Mathematica and MATLAB, which is famous with the metrics. Basically, we can do. Again, this is the disclaimer. I try to the best, but I take the material from the reliable source. But again, there is provide as is, and you can read the disclaimer. Okay, and then I guess just give 5 seconds that this is my background, the experience using programs, and I'm not again computer science. I'm not an engineer as well, so my work. So the assumed knowledge. So please have a look a little bit. So you need to understand a brief matrix algebra, for example, in the on Woodrick, just a basic or perhaps high school, yeah, depending on your level. And there are some R, Julia, Mathematica, and MATLAB here. For open source, again, it's free. For the proprietary commercial, there are free trial. Okay, so you can have a look, and this is the details of reading. So basically, I took materials from Hanson. I follow the Hanson, the econometrics graduate level appendix. That's mean for the master or PhD students here. And then some equivalent materials you can also find in the green econometric analysis appendix, online appendix about the metric. Okay. So another textbook also see here the filler, the basic multi-algebra with R, or Hamilton focusing on the time series analysis, or Brooks again, introductory econometric for finance. Another graduate level is Hayashi, econometric appendix A. Friend Sabo explaining linear algebra using Mathematica, details using Mathematica. And in Verbeek with econometric, there are also appendix on the metric algebra as well as the Woodridge introductory econometric. So you can have a look for a while. Okay. So now, as you can see here, let's continue. Okay, so this is the topics. The topic now is much more challenging than the brief metric algebra in my previous video. This is, again, the intended materials is for the graduate level of econometrics. So we will discuss notations, example, addition and multiplication in the first part. The second is the determinant, trace, inverse, orthogonal, and orthonormals matrices. The third part will discuss the eigenvalues, positive, definite, independent, and singular. The fourth part, decomposition and application of the solving linear systems. And the last part is the Kronecker product and the but I skip here, so I think just Kronecker products and property. Sorry, yeah. Okay, product and property. So let me update. Yeah. Of course, some of the material are theoretical, so I didn't include in here. But again, I give the illustration in the 4 software, R, Julia, Mathematica, and MATLAB, to give you understanding how to implement those theorems in metric theorems in computing software. So let's start by the notation, example, addition, and multiplications. Okay. Okay, so I move to the R code here. So the first section is discussed. So let's remove all. Wait, let me see. Yeah, okay. So let's remove all here. So let me make it bigger. Okay. Okay, yeah. So the output is here. So okay, let's start by the notation is you can see this is 2. You can make AA1 matrices. You can make so AA3 matrix. And you can combine AA1, 3, row bin, combine here with it. There is a okay with Yeah, okay. Sorry, there was a mistake. So let me correct here. So this is, yeah, so you can see the AA13 and AA1331. Yeah, the dimensions, okay. Robin, Columbine, and then you can make the identity metric here of 2, 2 and 3, 3. And then you can make as a matrix diagonal AA1. Okay, you can make this one. And then this is symmetric. So if you know that the symmetric here, so let me little bit of the matrix. Okay, so you can see when the symmetric, yeah, so you can see when the transpose, a metric is similar with its transpose, so we can say it's symmetric. So you can try here, test, and then using the logical value. Yes, true, true, true. So when all components. So this is the implementation in the R. Again, the next, let's see how we implement the Julia. So I show you the all Julia codes here. Okay. So you can have a look here. Yeah, let's go to Julia. Okay. So let me show here. So you need to use the linear algebra package here first. Okay. Yeah, let me, okay, good. Julia, we can make it bigger. So let's start by 2, AA1, AA3. Yeah, you can see factors, and then you can try transpose. Okay, there is sometimes. Yeah, okay, transpose, you can see also vertical and horizontal. You can see pretty easy. Okay, yeah, and then also, yeah, identity metric, diagonal, and then let's try the last is the symmetric matrix. You can see. Okay, also true. Well, that's in the Julia. The next, how we implement in Mathematica Wolfram. So now you can see here. Okay, so let's see by clear all first, and then notation 2, metric form, you can see the output here. So also AA1, AA3, transpose matrix. Okay, we transpose. How about the joins? Vertical and horizontal. So, and we can also make identity matrix. So you can see this is the code. We can also make the diagonal matrix here. And again, for a symmetric matrix, you can see and then transpose. So the matrix, if the transpose of a matrix is equals the metric, it's asymmetric. Okay, how about the MATLAB? Yes, you can also do. So MATLAB is famous strong for the metric. So that's why the name is Metric Laboratory. So let's see, you can see again here. Ooh. Okay. Okay. Okay, you can start here. So you can see there are some similarities, even they are different. So you can go for the transpose and then vertical category, horizontal, identity metric, diagonal, diagonal metric here, and also the symmetrical metric. So you can see. Okay, so the next is, oh yeah, there is also additional, okay, the next is associative and distributive. So you can see here that the, okay, let's go to R, A, B, C, okay. Here, so you can see A, uh, A, B plus C equals A plus BC. So you can see the same. So matrix A and 3 multiply A. So you can see scalar is the scalar multiplication. So, and then AB, so you can see this is the example. So AB multiplied CC, sorry, AB multiplied C equals A multiplied B and C first. So this is the, you can see this is the properties of multiplications. We can, which is we can see the name is, wait, let's see. Okay, so yeah, so this is the associative and distributive. So you can see also here. So the true mean the same here. Okay. So associative and distributive. Even the multiplication is not commutative. Okay, so how we implement in Julia? So again, we can just test. Where is the Julia here? Okay. Let's go to the Julia code here. Okay, so we can test as well. Okay, you can see the code. You can also, yeah, okay. So this is, yeah, there are some variation again. Please pay attention. The variation, similar but different. Yeah, okay. Oops, sorry. Oh, yeah. Okay, before I have one. Okay, now it's true. Yes. Okay, so I missed one. Yeah, okay, so you can see. And then how we implement in the Wolfram. Okay, so you can see here, associative and distribution. You can see this is the code. Okay, BB1, BBC. So let's see, AB equals A plus B, BC equals B plus C. So ABC is AB plus C should be equals A plus BC. You can check. Okay. The next is the multiplication matrix with the scalar. Now, how about the A multiplied B and then B multiplied C? So we test A B multiplied C and A multiplied BC. So the result is the same. And how about A multiplied B plus C should be equals A multiplied B plus A multiplied C. You can see. Okay, then let's go to MATLAB to prove here. Where's the MATLAB? Okay, you can see, yeah, okay, associative and distributive. Let's go create a matrix. So ABC. So you can see AB plus C and A plus BC, they are the same. Okay, so scalar multiplications, and then AB, which is A multiplied B and then multiplied C, should be equals with A multiplied in brackets B and C. So also A multiplied B plus C in brackets would be equals A multiplied B in brackets plus A multiplied C. Okay, let's go to the interesting part. Where is it? Yeah, this is more tedious because it's more theoretical. So that's why the level is the 4th grade with metric. Graduate econometrics. So the next is determinant trace inverse. Yeah, this is addition molecule. We finished. So determinant trace inverse orthogonal and orthonormal. So this is definition. Again, orthogonal, you can read the information here. So basically is the terms of orthogonal if a orthogonal and orthogonal matrix. So you can see, let's see, where is it? Go to R. Okay, so determinant, so it's pretty simple. So let's go to the determinant property. So you can see here. Yeah, in the R, sometimes we need rounding because again, there is no exact number except Wolfram Mathematica. So in this case, you can see I need to do some rounding. So you can see the property determinant of A and determinant of transfer A should be the same. Determinant of 5 multiplied A should be 5 to the power of the power of the n, and then determinant A. Determinant A and B multiplied B should be determinant B multiplied A. Inverse of determinant of an inverse should be 1 divided determinant of a matrix. Okay, so how about trace? So you go to the library sites here. Okay, you can see trace of matrix 2 and scalar should be equals to 2 multiplied transpose of matrix, and then trace of a matrix should be equal to the transpose of the trace of its transpose. So the transpose of D and E should be equals trace of D and E will be equals to trace D plus trace E. And then the trace of identity is the dimension of it. So 2 and 3. How about the multiplication? So the trace of metric 1 and metric 2 multiplications will be equals to metric 2 multiplied metric 1. So you can see even the metric 1 multiplied method 2 can be different with the metric 2 and metric 1. So inverse, you can also use the, in addition of solve function in R, you can also use the library MATLAB. So you will get the inverse, which is similar to the MATLAB. So you can see a1 multiplied inverse is identity. So that's the name of inverse. When a metric is multiplied by the inverse, the result will be identity. So the transform of inverse will be the same of the inverse of transpose. And then, okay, inverse of A and C will be similar to the inverse C multiplied inverse A. So this is another rules here. You can see this is a bit long. So you can have a look. So this is a longer. Inverse A plus C will be equals inverse A multiplied by inverse A plus inverse C in bracket, the inverse of inverse A plus inverse C. And then after that, multiplied by C1. A little bit complex. Oh, sorry. Where is it? Okay, so is that any mistake from my side? Okay, yeah. It's a bit longer. Sure. Okay, so let's see. Oh, wait, too long. Okay. Yeah, okay, that's really okay. So it's good. So this is another inverse A plus C. You can see equals inverse A multiplied inverse A plus inverse C and then inverse C1. So another is inverse A minus inverse A plus C equals inverse A multiplied inverse of inverse A and inverse C multiplied inverse A. Orthogonal on orthonormal here, so you can see here if the it's multiplied matrix, so the inverse will be similar with the transpose. You can see here. Okay, so this is the name of orthogonal and orthonormal here. There is a Woodbury metric identifier. This is a bit more complicated. So suppose there are 4 metric. So you can see the inverse of metric E multiplied F and G and then H will be equals or inverse E minus in long brackets inverse E multiplied inverse E multiplied F multiplied inverse of the inverse G plus H multiplied inverse E and then in brackets and then multiplied F and then after that the inverse multiplied by H multiplied inverse E. Ooh, quite long. Woodbury metric identifier. Okay, so where is the last here? That's the R. Okay, let's go to the Julia. We can also use in Julia as well. Okay. Let's see. Yes. Okay, let's go here. Determinant, you can see standard of, yeah. Okay, you can see determinant, yeah. Correct. The same. So the next determinant you can also prove. The trace similar, just the variance of the code. Transpose and then trace of transpose, you can see the similar with this here. Okay, so and then let belong. Okay, okay, you can find. And then how about the inverse? You can see transpose of insert. We can also prove. Even there are a little bit variation and we might to use the rounding. But in bracket, it's the same, yeah, just because the statistical and rounding differences in the system. Yeah, so you can see even a bit more complex we can go, and then orthogonal and orthonormal, you can see here, okay. And then again, the challenging or difficult Woodbury metric identifier you can test. Okay. Yeah, true. All right. So the next is, what is? Wolfram, let's see. Determinant property, you can see this determinant. And then the determinant of transpose, you can see, yeah, it's clear. However, sometimes you need to write something long like dimension, then inverse, trace. Okay, trace is TR, the same, yeah. Okay, tries to digits, which are you can see the same. Wolfram true, okay, transpose D, trace of transpose and trace of D will be the same. If D is D plus E, so the trace of DE should be trace of D plus trace E, and so on. So you can see trace of identity will be similar to the dimension. So how about the metric multiplication? Again, you need to write dot here. So the of dot trace of dot F1 and F2 will be similar F2 and F1. Even the F1, F2 will be different of F2, F1. But the trace are the same. How about the inverse here? So you can see A multiplied inverse of A will be the metric identity. So the transpose of inverse A will be equals to the inverse of transpose A, and so on. Let's go here. Again, if you want to know, you can stop in the part and you can try your own and try to understand to learn about the metric theorem and properties. So let's go to orthogonal and orthonormal here. So you can see the dot multiplication of H and transpose will be the metric identity. So inverse H will be equals to the transpose. So this is the orthogonal and orthonormal. Again, we try to apply the Woodbury metric identity. So you can see E, G, F. Yeah, sorry, it's not in order, but anyway, still correct dimension. So inverse, this is long, and another long formula here. And this is the Woodbury we can prove. Okay, how about the MATLAB? MATLAB here, okay. Okay, so let's go to the determinant first. Yeah, so you can see this is the code. Yeah, it seems the MATLAB is the quite simple, yeah, in the term of metric. Yeah, that's because the why the MATLAB is used. Okay, so this is as a trace you can test. Okay, work, see the output. So yeah, we can prove the property of inverse as well. Pay attention on the variations here. In principles, they are the same. So that's why the theory of metric is important. We can prove. Okay, orthogonal and orthonormal. And then the last is the Woodbury metric identity. So, and then this is the long proof, but we get true. Again, which is true is 1, 1, 1, 1. Okay, so let's go to the next. The next is the eigenvalue, positive, definite, independent, and singular. So let's start by the explanation in the R. Okay, eigenvalue, R has the system like eigen, and then there are sub-factors, values, and factors. So you can check the determinant of eigen equals the product multiplication of the all eigenvalues, and the trace of eigen of a metric will be equal to the sum of the eigenvalue. Yeah, you can see it's true. You can also see, and what is the positive definite when the eigenvalue of a matrix all positive? So it's true. Okay. And then what is idempotent metric? When you multiply a metric multiplied by itself, it's become it's metric again. And singular metric is when the determinant is 0. So when the metric singular here. Okay. So yes, this is quite a lot of materials here. Okay. Okay. Let's see. Okay, so that's with okay, let's go to the next. Okay, so after R, let's go to the next. Where is it? Julia. Nice. Okay. So let's go to eigenvalue. So the formula has some differences, variation. Oh, it's work here. Eg false, egg false. Yeah, okay. So yeah, we can again also prove. determinant trace. Okay, you get it. So round. You can make, okay, positive definite. You can also try. There is functions is postdef and then idempotent and then singular. Just calculate the determinant. Okay. Okay, the next is the Mathematica Wolfram. Okay, so eigenvalue, let's see, eigenmetric one, okay. Yeah, so you can see the property are the same, just difference in the code. Now they have the eigen system in the Mathematica codes. So the positive definites you need to try to, there is functions in the Wolfram positive definite metric. So you know whether it's, sorry. Okay, so, and then idempotent, you can see here, okay, true. And singular metric, check the determinant symbol. Oh. Here. Okay, so then the last, let's go to the MATLAB. Eigenvalue. Yeah, this is the this is the syntax here. So eigen, they will produce the to phi and d. Okay, okay. Positive definite here, you can see the, you need to extract for, and then you can see the eigenvalue, which is d, the d component, the right side. You know, this is the left and this is the right. So this is eigenvalues and this one is the eigenvectors. Check all the diagonal is okay, true. About idempotent here as well as for the singular. Okay, now let's go to the next, which is interesting. So, oh, sorry, where is it? Okay, decomposition application. We learned to decomposition the Cholesky and KR, and then how we can solve the linear system using those decomposition. So let's go to the R. Okay. Again, the formula might have some variations because how the software present might have simply different. In the R unit library metrics. So let's go suppose there are the simple for Cholesky and KR here. And then the application, again, for example, there are matrix of A, B. So you need to transpose the call of A matrix, A size here, and then lower triangular and upper triangulars. And then you calculate Y, which is the inverse of lower triangular, multiplied the B. B is the right-hand side. And then you can find the X solutions with the inverse of transfer of lower triangular multiplied C. So this is the formula in the matrix. You can use using key area, and in this case, you use the solve function. So solve key assist, and then so you get quickly. Yeah. This is again in R. Okay, so the next in what is Julia? Yeah, you can also use the Julia as well. So this is quite nice. So the composition Cholesky here, so you can see there are three metrics key R. You can get simple using the key area. Okay, so let's try to solve using the Cholesky. So there are minor variations, but in first transpose of Cholesky assist multiplied is the lower. In principle, it's similar. You get the same. Okay. So, but key R, you need to compose key and R, and then the solution is the inverse of R component, and then transpose of Q and then P. You get the same result. You can test if you want. Let's test the solution. Okay, have you test on the R as well? Oh, okay, no, fine. The next is Wolfram. Okay, so you can see the composition. Let's see. Here is the metric. So Cholesky. Oh, sorry. Stepping from. Yeah, the compositions, and then you get it. And Cholesky and then KR. You get, okay, solving linear system. Okay, let's see. Oh, Okay. Positive test first, positive there, then collapse transpose, and then lower triangularize. It's pretty simple, and then upper triangularize, and then by size you get, and then you can get the X solutions. You can report the metric form. How about the key R? It's the same. Yeah, this is the exact number, and then you extract the RCs, and then you dot the multiplication of inverse R and Q, and then multiply the P. You get the TR. We can also do the test. Okay, and then let's go to the MATLAB. How we implement in MATLAB code here. So you can see the decompositions here. Okay, tallest key, you can see tall, lower, and upper, the manual here. Key R is QR, and then you will get the key R. So you can solve it using tallest key multiple. Again, pay attention on the formula there, A, B. Okay, so you get it, the solution the same. Okay, -5, -4, and 2. Pay attention on this formula. And then QR, you can also find here. Okay, you can do also the test. Let's see here. So be the same. Okay, let's go to the last part. This is another last part here, which is Kronecker and the property of Kronecker. Okay, so let's start by the R. Okay, Kronecker product. Suppose there are Kronecker A, B, C, D in this metric example. So Kronecker A and B, Kronecker C and D. You can see. So the properties you can see here, Kronecker A plus C, and then Kronecker between A, C, and B. A plus AC means A plus C will be equals to Kronecker A, B plus Kronecker C and D. The second is the Kronecker of A and C multiplied Kronecker B and D will be equals to Kronecker A and B and then C and D. And then Kronecker A and Kronecker B and C will be equal to the Kronecker of Kronecker between Kronecker A, B, and C. And then transpose of Kronecker A and B will be equals to the Kronecker transpose A and transpose B. Trace Kronecker A and C will be equal to trace of A multiplied C. Okay, so this is the inverse. This is a bit long, very long. Okay, so you can find that the inverse of Kronecker A and C will be equals to Kronecker inverse A and inverse C. And then determinant of the Kronecker A and in brackets Kronecker CD will be equals to the determinants A to the power of the dimension of the Kronecker CD, and then determinants Kronecker CD multiply the determine dim of dimension of A. Okay, we finished. Let's go to on the implementation in Julia. So Kronecker product. So let's see unit 2 menu, which is called using Kronecker. Okay, package. So your Kronecker is pretty simple. Again, you can see, you can also get the size. Then properties, again, you can see the, I think pretty similar. Just now is different variation. You get through. Okay, yeah. You get quickly. Okay, so we finish our version. Okay. And then the next is the Wolfram. Let's go to the Wolfram. Oh, where is the Wolfram? Okay, so Kronecker E, yes, okay, A, B, C, D metric. Okay, so the Kronecker is A, B, C, D. So this is the property. So you can see this is also, we can also prove. Yeah, okay, a little bit long, but it's quite clear. So the built-in function, it's easy to prove it. Okay, so the next is the last. Let's try to the MATLAB. Okay, here Kronecker again, you can also see here. Okay, so cron, the function is cron, K-A-R-N, and then let's prove the property. But in MATLAB, a little bit complicated because you need to make an object of the size first, dimension, and then you power. Okay, that's correct. So I think we have ready Finish. So okay. So again, this might be useful, especially if you want to learn the complex metric algebra in the graduate level of econometrics. Okay, thank you very much.